I need to get some pieces.
Dude, I don't even mind singing your Angel. It's my girl that we've sang 50.
How does that go?
Oh boy. Talk about my girl. My girl.
Yeah, that one.
Yeah, so my girl, my guy, I think is probably, sounds like.
Alright. So where did we actually finish up yesterday?
After hydrogen bond, we just finished
Okay.
bond fold, I think.
Yep,
Pretty-
we got through that part.
So I threw a lot of review at you yesterday, and I took quite a bit of time going over that review. So I just want to highlight and summarize what we talked about yesterday. Okay, we have inter and intra. Difference. Talk to me.
Inter is
If it's intra
in
is
between
trouble.
the molecules themselves.
All right, sorry.
Yeah.
Let's raise your hands so that I don't hear like 5 different things at once. I don't want to, like, a lot of you were saying correct things, but I couldn't really focus on any one of you because you all were not. Go ahead.
Intermolecular is the bond between molecules, intramolecular is the bonds within molecules.
Okay, so within, that would be your chemical bonds, right? If we were doing a Lewis structure, that would represent your dashes, right? Okay? Your inter, then, is between, so it's the force that holds molecules together. And what does that affect?
Electronegativity.
No.
Phase.
The phase it's in. Right? Think about it. If we're talking about the force that holds molecules together, isn't that the force that's going to hold them in the solid state? Or the liquid state? Or the force that you would have to break to get to the gas state? Does that make sense? Everybody? Okay. Then we talked about which one's stronger. Raise your hand. Which one is the stronger? Revan.
Intra.
Okay? And that's because just common sense tells us that we can go from a solid liquid to a gas a lot quicker than breaking apart hydrogen and oxygen of a water molecule. Make sense? Right? Then we talked about 2 of the 3 types. Okay? What was the first one we talked about?
Dipole.
Dipole, dipole. And, okay, that was a kind of a loaded concept. Well, let's say we have HBr. Okay? We went all the way back to talking about electronegativity. Correct? Okay? And the reason why we talked about electronegativity is because it's the electronegativity difference that creates the what? The polarity. And it's the polarity that gives us the charge that can cause the attractive force. Does that make sense? Yeah. Okay, quickly reviewing. So what we had was, in this particular situation, we have which one that's more electronegative? Bromine's more electronegative. What does that do to the electrons in here? Goes towards closer to bromine. When you have a shift of negative things that way, it creates a partial charge. Where is the partial positive charge? On the hydrogen. And the partial negative charge is over here. Now, listen to me here very carefully. The bigger the difference in electronegativity here, the stronger these charges are. Does that make sense? You have a bigger charge distribution causing a stronger charge. Stronger charge is going to give you a stronger intermolecular force. Let me show you what I mean. What the molecules will do, they will originate or orient themselves so that the positive things are attracted to the negative things. Right? By nature, they're going to orient themselves so that they have the most maximized attractive forces and minimize at most all the repulsion forces. Okay? So what we have is electronegativity, which creates polarity, and it's the polarity which causes the what? What is this attractive force called? Intermolecular force. Okay? Then, we specifically talked about dipole-dipole, which says it has to be a polar molecule. Okay? But there's a certain class that is a stronger version of a dipole-dipole. What do we call that? Hydrogen bond. Okay? So let me give you one that would be a hydrogen bond. Very similar. Is this still polar?
Yes.
Is it still a partial positive and partial negative?
Yes.
Still orient themselves so that the positive is attracted to the negative. All that stuff is exactly the same. Same type of attraction. The only difference between a dipole-dipole attraction and a hydrogen bond attraction is that this particular intermolecular force here, this attractive force, is stronger. Okay? What causes this force to be stronger than this force?
The electronegativity of fluid.
There's a bigger difference in electronegativity. And we said the bigger the difference in electronegativity, the stronger these charges are. Stronger charge should make sense. It's going to give us a stronger what? Stronger force. Stronger intermolecular force. So, of these two, this or this, which one do you think is more difficult to get to the gaseous state? Because it's a stronger bond, so it's going to take more energy to break that bond. Got it? A little quick review. A little tougher night you had last night? That might be your problem.
What?
It's not so much that you don't get sleep that causes you to be tired, it's when you change your sleep patterns.
That is true. Like if I go to sleep earlier than I normally do, I feel more tired.
Yep, absolutely. So if you're gonna not sleep, consistently not sleep.
That or slowly adjust.
Yeah, slowly adjust it. Or just expect that you're gonna feel tired the first couple times you do it. Alright, now.
No matter what.
What?
What if you feel tired no matter what?
What if you feel tired no matter what?
Yes.
Maybe you have sleep apnea. I don't know. Alright, last type. So we talked about 2 of the 3 types. This is actually probably the most difficult. Okay? Because what a dispersion force is, first off, everything has the capability of having a dispersion force, but we specifically focus on dispersion force when we're talking about nonpolar molecules. Okay? So let me give you an example of a nonpolar guy. Methane. What was the one way that we used to determine this is a nonpolar guy? We had a test. Do you remember what it was called?
I remember the test, what it was called.
The symmetrical symmetry test.
Oh, yeah, like
Remember that?
draw a line.
Cut it like this, cut it like this. If it's a mirror image on both sides, both ways, it's going to be nonpolar. Okay? Does that mean that there isn't distribution of charges? Not necessarily. Let me show you. Hydrogen and carbon do not have the same electronegativity values. In fact, carbon, I think, is a little bit more electronegative. So what that means is that the electrons are all kind of pulled towards the carbon. A little bit. Not a lot, but a little bit. Make sense? So technically my negative region is right in the middle. And my positive regions are all on the outside. Well, is this polarity? What is the definition of polarity?
Opposite regions of opposite charge.
These do have opposite charges, but are they on opposite regions?
No.
No. Here are my 2 opposite regions, and they're the same charge. So yes, there is a charge, but it is in opposite regions of opposite charges. And here's the problem that this possesses. Okay? If I were to bring another methane molecule up close, that's going to be partially positive. What's going to happen?
We're not gonna go together.
They're not going to attract. This is why methane, naturally, is in the gaseous state. Should make sense, right? There's nothing to attract it, so it's not going to be in the liquid or solid state very likely.
Why did it stay at the gas though if there's nothing to really keep it? Oh,
That's why it stays at a gas, right?
yeah. But like if there's no attraction whatsoever, why would it stay together?
It won't, typically. However, I want to show you that methane you can get to become a solid or a liquid. Right? For example, CO2. That's nonpolar, correct? If I were to draw CO2, let me just quickly draw it for you. Nonpolar, correct? Okay? Well, you'd have the same problem you would have here. Have you ever heard of dry ice? That's the solid form. So, even though there's no attractive force here, how in the world did CO2 get in the solid form? Because there's got to be some force that holds it in the solid form, and we know it has to be intermolecular forces, correct? This is where the mind gets blown a little bit. Okay? Here's where the dispersion forces come in. It says an electrostatic attraction, that's referring to this, even though this is not going to attract. Okay, arises between atoms or molecules because of the presence of a. That probably is extremely wordy, and maybe you're not following that. Let me kind of explain what actually happens. Okay, electrons are moving, correct? Kind of rapidly and randomly, right? Is it possible that the electrons in here might, just due to sheer probability gauge, okay? Sit up, bud. Can't let you sleep. I'm sorry. I know, and I'm sorry I'm boring you, but I'm not going to let you sleep. Okay? So, these electrons in here, just due to sheer probability, is it possible that temporarily that like some more electrons could be on one side versus the other? Is that a possibility? Everybody?
Yeah.
Okay? So what actually ends up happening is what you have is that temporarily electrons might shift. Now this is an outrageous example, but they can shift to one side, which really ends up creating a temporary dipole. But then what ends up happening is the dominoes all start to fall. What do I mean by that? If this side's positive and this side's negative, a neighboring molecule is going to have its electrons shift in a way so that the negatives of the other molecule will shift away because it's not attracted to this negatively charged side here. And what you end up having is one guy creates the domino effect that creates dipole with everybody. You're leaving now?
I have to.
Okay.
I don't want to.
I have the video going, so I'll try to post that.
Okay.
So everybody hear what I said? Kind of crazy. But in non-polar guys, just due to sheer probability of electrons not being, orderly moving around, they can create their own dipole. Create their own polarity. Because, does this make sense that if I had another molecule here, actually let's just start here, okay? Technically, let's say these are perfectly uniform, okay? If this comes near this positive charge here, what are these electrons going to do?
Move away.
Away from the positive?
Oh, they're gonna move.
They're going to
more
move
to the
this way, aren't they?
Yeah.
At least a little bit. Well, what's that going to create?
Attraction.
It's going to create polarity. This is going to start becoming negative, and this is going to start becoming positive. Well, what's going to happen to then the other guy over here?
It's gonna be
the same thing. And the other guy over there, the same thing. So what ends up happening is you create this domino effect where now polarity is created due to a random shift of electrons in one guy. Now, does this happen easily? No. Methane normally, carbon dioxide normally, is in what form? Gaseous form. That's where it's naturally most stable. But if you start compressing things, can this happen? Like methane, gas molecules are probably never going to come close enough where this is going to happen. But if I compress a gas, slow it down a bunch, so that they're next to each other, can this happen? Yes, absolutely. This, I believe it's on the previous slide, we say it's the only intermolecular force that's going to be the result of nonpolar molecules. Now, what's really interesting is this dispersion force is the weakest of all of them, in most cases. Here's when it can be stronger. When your molecule is large. Any idea why dispersion force could get relatively strong if we're talking about a really big molecule? Say that again?
Electrons have a looser orbit.
Okay. Okay. Good guesses. Not right, but that's okay. Here's why. They have more electrons. More electrons can create more charge imbalance, right? More charge imbalance is going to mean stronger intermolecular force. So, the bigger your nonpolar molecule, the stronger your intermolecular force is going to get. Let me show you what I mean. Right? This guy, methane, is a gas at room temperature. Relatively small molecule. We talked about it. It's nonpolar. What's the only intermolecular force this will ever have? What's it called? Just talked about it. Dispersion. The only intermolecular force it's going to have is dispersion. Since it's a small molecule, it's going to have a very low amount of dispersion. Probably not enough to make it a liquid or a solid. So this guy's naturally a gas at room temperature. Get a little bit bigger molecule, same type of atom, still carbon, still hydrogen, much bigger molecule, a lot more electrons. This guy's actually a liquid at room temperature because it has a stronger dispersion force, strong enough to hold it as a liquid. And the reason why it has a stronger dispersion force is because it has a lot of what? Electrons that can create a stronger charge imbalance. Now I don't have room for the next one, but use your imagination. Octadecane, real big molecule, huge. This guy's actually solid room temperature, still made up of carbon and hydrogen. Wow, Gage. Just every once in a while, just move his, hit his arm out.
You put YouTube because it's still on there.
Yeah, it was too big to fit on there. Okay? Now let's summarize all this before we do this problem. I'm going to give you a little flow chart here that you're going to want to write in. Ready? You're going to have to determine what type of intermolecular force is going to be active. So you might have to go back to doing Lewis structures. So glad you guys are awake and alert and available. Okay, here we go. First question you need to ask. I'm just abbreviating. Okay, so this would be the first question you would ask when trying to figure out what type of intermolecular force a particular molecule is going to have. If the molecule is not polar, what is the only choice for intermolecular force it could possibly be?
Dispersion.
Dispersion. Yeah. Your book also calls it London dispersion. So if you read and you see that, don't be confused. Okay, they're the same thing. If the answer is yes, it is polar, you have to ask a second question.
Why?
Any ideas?
Does it have hydrogen? What's this bond in chlorine?
Dipole. Yep. They had to put a cutoff somewhere. If it's polar, you gotta ask, okay, do you have hydrogen bonded to nitrogen, oxygen, or fluorine? Now be very careful. You could have something like this. For example, you could see this particular guy. I could ask you, what kind of force is going on here? Okay, this one's actually going to be dispersion. But Mr. Kramer, I have hydrogen and fluorine here. Doesn't that going to be hydrogen bonding? Is hydrogen bonded to fluorine?
No,
No.
it's bonded to carbon.
That's important. When I say is hydrogen bonded to nitrogen, oxygen, and fluorine, it means in the Lewis structure, there's a bond between them. Okay? Just want to make that clear. If hydrogen is bonded to NOF, what would be your intermolecular force? If it is?
If it is,
Yeah. What's it called if it is?
hydrogen.
Hydrogen bonding. If it's not, it has to be what? All right. With this should help us be able to answer these questions here. However, sometimes being able to answer these questions results in having to write the Lewis structures of it. Dang it. Dang it. What did I do?
You get a squirt bottle, everyone does that.
Wow, I guess so quiet.
We're trying to make sure you were sleeping. Alright, so let me show you how you're going to go about doing this. Okay? Some of you might be able to just look at it and know. Okay? And some of you might be able to know just in your head what this Lewis structure is going to look like. Now, I already showed you the Lewis structure.
Well, I thought it was going to be bent 102.
It isn't going to be. Wow, so you're telling me not only do I got to remember how to do Lewis structures, but I also need to know the molecular geometry so that I don't make this bent when it needs to be linear. Why is that important?
Because that
Little
is
change.
polarity.
If I write this bent, it doesn't obey the symmetrical test, and you would say this is a polar molecule. But if I draw it linear, it does obey the symmetrical test, and it's nonpolar, and that's going to change your answer over here, isn't it? Okay? Quick little review. Two regions, both regions are bonded, a 2-2 is linear. So, what is going to be the type of intermolecular force for CO2? It's going to be your dispersion force. Okay? The next one's real easy because it's just two guys bonded to each other. And it is hydrogen bonded to fluorine. What's the answer for the next one? And you can probably guess what the third one is. This is going to be polar, So, is it a polar molecule? Yes. Does it have hydrogen bonded to NOF? No. It has to be what? Which of these three is most likely to be in the gas form?
CO2.
This one.
CO2.
Which one is most likely to be in the solid form?
HF.
Yep. Because this is your strongest force, that is your weakest force. Now, does that mean always and every? No, because we did. They're actually, guys. If you get a strong or a big enough molecule, you can actually get dispersion force that's stronger than a hydrogen bond.
Wow.
Hence why you saw that huge molecule that I gave you earlier that I didn't show on the board because I didn't have enough room. That's why it was a solid. Now, I want you guys to try to answer this one. Okay, it says based on the bonds that are within, predict which is going to have the higher boiling point. So I want you to tell me which one's going to have a higher boiling point. I want you to kind of give an explanation as to why. This one is taking intermolecular forces and applying it to boiling point. If you can get this right and get the reasoning right, you have a very good grasp of this. Yeah? Need help? Okay. Which one has the biggest difference in electronegativity? No. Why don't I go through it? All right? Okay, I'm going to go through the rationale behind this. Okay? First off, maybe the very first thing you should try to identify is what type of intermolecular forces you have. Okay? You gonna leave?
No, just tuck in the shirt.
Okay, let's just start with this. This one might actually be pretty difficult. We know that this is going to be what type of intermolecular force?
That is good.
Persian.
It's non-polar?
Oh,
Dipole.
yeah.
This has dipole. Now this one is actually something we haven't kind of talked about. What is the main difference between this and this?
Well, one has a solid in it.
Ah, one's ionic.
That one.
This is ionic. Let me give you a little hint.
Ionic stronger.
It has to be.
In ionic compounds, the inter and the intra are the same. Because in ionic, do you have distinct molecules? No, you have this huge structure of ions. Do you have partial charges? No, you have complete charges. Why do we say complete charges? Because it's a give and take. So, if you ever see ionic, it will always have the highest boiling point. Because what you are really doing is you're breaking the bonds within. Now, you're probably thinking, well, can you do that? Yes, but it would take like thousands of degrees Kelvin to be able to do this. Okay? So that one, maybe I would expect you to not have probably got. Okay? Because I didn't talk about ionic. Okay? So this guy's going to have the higher boiling point because you have to break intra forces. Okay? This one maybe you should have been able to get. What kind of force is here? Over here. Everybody understand why this is dispersion and this is dipole? Okay? Alright, Tanner. This is dispersion. This is nonpolar. Alright, if I got chlorine bonded to chlorine, they have the same electronegativity values. You can do the symmetrical test, you can do it all, nonpolar. Make sense? These are just iodine bonded with chlorine. They're two different things. They have two different electronegativities. So it's polar, but it's not hydrogen bonding. Okay? Now, based on this, which of the two has the higher boiling point and why? Raise your hand. Go ahead.
I put iodine chlorine because it's like it's got like it's harder to break it apart.
Why is it harder to break apart? You're right. Why?
Because it's more polar.
It has a stronger intermolecular force. Yeah, absolutely. This is going to have the higher boiling point. Okay? It's going to have the higher boiling point because it's got a stronger force that's holding it together. And so it takes much more energy, aka a higher temperature, to break that bond. Does that make sense, everybody? So, if you've got a choice between hydrogen bonding and dipole, which one is going to always have the higher boiling point? The hydrogen bonding. Okay? Because it's a stronger force that holds them together. Lastly. Alright, so basically what I want you to do, I want you to try to do this on your own. Try to figure out which type of intermolecular force it has. That's your help. You will have to do this in your homework. So it's polar. Why is it polar? Okay, can you draw the Lewis structure of that just to prove it? Okay, all right. Not symmetrical or non-polar? What are we on? So you're, yep. I'm coming. Okay, and then little next step for you guys, once you have identified, maybe tell me which one you think is most likely to be a gas. Okay? I want you to answer these two questions. Which one's most likely to be a gas? Which one is most likely to have the lowest boiling point? The lowest boiling point. I wrote kind of sloppy there, but. You have a question?
Yeah.
I'll explain to everybody here. If you don't know quickly, then let me just explain to everybody.
Those four.
Yeah. Okay, first up, I want to go through the process of figuring out what type this is. Lewis structures are kind of important. If you can do Lewis structures, you can see that this guy is going to follow the symmetrical test, which means it has to be what? It has to be dispersion because it's nonpolar. Make sense? Okay? If you were to do this. Lewis structures, again, pretty important. Voila, voila, voila. Well, it doesn't follow the symmetrical test, so it has to be polar. Is it hydrogen bonding or not? Yes. It's hydrogen bonding because you have NOF. Okay? This, if I do the Lewis structure, it's definitely going to be polar. And dipole-dipole, don't leave. Same thing here, it's polar, but hydrogen bonding. Now, which is most likely to be a gas? You guys said what? H2, that is correct. Which is going to have the lowest boiling point? Also H2.
That's what I thought.
Guys, if this is most likely to be a gas, it's going to have the lowest boiling point to become a gas. That make sense?
Yeah.
The reason why I didn't say highest boiling point is because you wouldn't have known which of these two would have the highest boiling point based on the information you know. Okay? Hopefully 2 days helped to at least solidify that a little bit better than 1 day would have. Alrighty. Come see me if you have questions.